So, very good evening to all. So, thank you for joining one day workshop on FPGA. So, good evening, Manikanta. So, thank you for joining. So, is my voice is clear? Can anyone respond in chat box? If my voice is clear, just put OK in chat box. Then only I can know if my voice is clear or not. So, if my voice is clear, can anyone respond in chat box? Sai Manikandan, you can respond. I'm audible to you. So, okay, thank you, Manikandan. So, very good evening to all. Thank you for joining. So, nearly some people is there. So, let's wait for a few minutes. So, remaining people have to join. Then we'll get into session. So, let's wait for a few minutes. So please wait for a few minutes. So remaining people have to join. Then we'll get into session. So we'll start at start 4:05. So at the 4:05 we will start the session. Okay. So let's wait for a few minutes. So today we are gonna see FPGA. So how FPGA design flow works. So how FPGA is helpful for us. So what are the benefits FPGA. So how to write the Varilla code for that. So how to create the project in Intel Cortex Prime and Xilinx. So we'll see in this session. So let's wait for a few minutes. So is my voice is clear or I increase my voice? It's clear for you guys. May I know that? So very good evening to all. Thank you for joining. So thank you for joining one day workshop on FPGA. So today we will go to see a lot of things on FPGA. So please stay in the live session. So you will get the more knowledge in FPGA. So may know the how many students are there pursuing UG degree. May know that. So in this session we will see the Verilog basics and how to write the code for digital circuits like a full adder, half adder, flip-flops like a T flip-flop, JK flip-flop. So we will see the Verilog execution and then FPGA design flow. So then how to create the project, how to create the project in FPGA like using tools like Xilinx and Intel Cortex Prime. Yeah, okay, Mishra. Thank you, Mishra, for your response. So let's wait for 2 minutes. So we will start at correct 4:05. So today we are gonna see FPGA, Verilog, and then Xilinx, Intel Cortex Prime. So these are the topics we will cover in this session. So before going to that, I will explain the chip. What is chip? What is inside the chip? Why? Because of VLSI is fully based on working on chip. So we are the VLS engineers are working for the chip performance. So why? Because of the evolution of AI, this smartphone, personal computers. This all based on the VLSI technology only. So we'll see the chip basics. So what is inside the chip? How it works? So how the embedded engineer work with the chip, so how VLSI and embedded engineer work together for the making chip. So we'll see in this session. So once again, thank you for the people who are joining this workshop, YouTube live workshop. So thank you for joining. Welcome to Pantech. Okay, so I think we'll start the session. So before going to the enter into FPGA, so I want to share something about chip. So what is chip? So can anyone respond in chat box? So what is chip? So what is inside the chip? So what is the literal thing? So what is the inside the chip? It having something inside the chip. So may know that. So can anyone respond in chat box? So what is inside the chip? So how chip works? So you can respond freely. So you can anything. If you have anything in my mind, you can respond in chat box. So basically, inside the chip, it having the transistors only. So by using the transistor, so by building the transistor, a number of transistor onto the single silicon, it's like a chip. So this is a VLSI motive. So very basic thing of VLSI is we need to make a chip. So VLSI is one technology. By using that, we need to make a chip. That particular chip must be power efficient, high speed, and then compatible means we have to make the chip in small size. So I will write down in some notepad, so it's like a notes for you. So I will open my notepad. So basically, so chip is consist of transistors. So transistor is a switching device. So we can use it for the digital to make a digital circuits, and then we can make the we can make the analog circuit by using the transistors. So most probably we are the chips are consist of CMOS transistors. So CMOS transistor is the it's comes under the MOSFET. So MOSFET is one kind of transistor. It having the NMOS, PMOS. So combination of the NMOS, PMOS is a CMOS transistor. So it's like it normally CMOS transistor works like an inverter. So this is the main thing. So normally CMOS transistor is works like an inverter. So it like if you given a CMOS inverter input 0 means you will get the output as 0. So I hope this is I know you guys know about the CMOS technology, CMOS transistor. So just tell me orally. So CMOS basic most of chips in the current era is based on the CMOS technology only. So it having the NMOS, PMOS, combination of NMOS, PMOS. Why we are using the CMOS transistor particular means it will give the by using CMOS technology we can give only less power. So less power, it's like a fast execution of the values. So it is faster than compared to FET, BJT transistor, and then normal FET transistor, and then MOSFET transistor. So it is faster than all these transistors. That's why we are using the CMOS transistor. It is faster than other transistors like a BJT, NPN, MOSFET, and MOS. So by using the CMOS transistor we can achieve the digital circuits. We can build any digital circuits. So we can make the all kind of gates by using the CMOS transistors. So we'll see in this session briefly how the transistor are made. So we are writing only Verilog code, and then that particular Verilog code is converted into gates, and then the gates are converted into transistors. So this is a design flow of FPGA. So we'll see in the one by one topic. So firstly I will start with chip. So chip is a one semiconductor. Chip is a consists of transistor. We can give the digital circuit to do the chip. So how means, so we can give complex circuit to get the output. So basically chips are everywhere, like a mobile phone, car, AC, TV, laptop, computers. So chips are everywhere. The VLSI engineer is main part of the chip. So basically VLSI is divided into two types. For making the chip we need two engineers. So one engineer called front end engineer. So front end and the back end. So like IT, we having the front end and the back end. So back end engineer. So we having the VLSI engineers, two engineers, front end engineer and back end engineer. So front end engineer works based on the Verilog code or system Verilog code. The front end engineer will write the design code for the chip. So we have the chip, that particular chip, it having the some transistors. So we need to use the chip. We need to use the chip. So by using the Verilog code we can assign the work for chip. So it's like a baby, it's like a child. So you have one child, it's like a chip. So you can give instruction for the chip by using the Verilog code, and then that particular chip will work based on your instructions. So this is a design flow. This is a main thing of chip. By using the Verilog code we can control the transistor working. So we can give the condition for the chip making. So by using these things only chips are made. Mainly front end engineer will do the coding part of the chip, and then back end engineer. So back end engineer will do the physical, will do working in physical chip, like how many transistors it may constrain. So how many logical blocks, so how many transistor, how many wires, so what are the how many IO pins. So these all things are taken by backend engineer. So working and then condition logic, it's all taken by front end engineer. And then making of the physical chip, architecture of chip, how many transistor in the chip, these all things taken by backend engineer. So this is a main two engineers who involved in VLSI technology, front end and back end. By using these two engineers only, we are using the chips. So this is the first thing. And then so front end engineer will write the design code for the chip. So design code is nothing but instruction for the transistors. So how the transistor will act. So this things is this designing code part will take care by front end engineer. So he will use the HDL language. So HDL is nothing but hardware description language. So HDL. So HDL is nothing but hardware description language. So by using the HDL language, we can control the chip. So for example, the HDL language are languages are VHDL, and then Verilog, and then system Verilog. So these are the main languages. It's like a HDL languages. So HDL is nothing but hardware description language. So name itself it having the hardware description language. So we are saying to the hardware how you have to work. So these things are written by the HDL language, like a VHDL, Verilog, system Verilog. So previously we have only Verilog and VHDL. So and now we also having the system Verilog. So system Verilog is an advanced language to design the chip, so to write the design code for the chip. So this is a main latest language of system Verilog. So Verilog and system Verilog looks like a C based syntax. So I hope you people may know the C language, C++, C. It's like a basic language, basic coding language. So by Verilog and system Verilog follows the same thing. So the same means the syntax of C and the system Verilog are same only. So syntax of C and the syntax of Verilog, system Verilog are mostly same only, but difference in structure. So how they use. So I will explain in the upcoming upcoming slides. So and then this is the main thing. So firstly we have two engineers, front end and back end engineer. Front end engineer will take care the design code and the verification of the chip by using the coding. Just they will do just doing the code only. They will cover the coding part of the chip, and then back end engineer they will work under the physical chip. So how many transistor, how many logical elements, so how many IO pins needed for the particular chip. So this is the main roles of the engineers, front end and back end. So back end engineer will work with physical chip. So the front end engineer will write the Verilog code, and then they will do simulation, they will do testing, and then they will say, so I have completed my design code, and then by using this design code you can make the chip. So and then backend engineer will take care of the code, and then they will convert the code into gates, and then gates into CMOS transistor, and then in the foundries. Foundry means like a factory. The factory, like a chip making factory, they will make the chip based on the front end and back end response, back end engineer results. So after that we are having the chip, and then post silicon validation. So there is another role is called post silicon validation. So that particular engineer will check the physical chip how it works. So they are checking, so it will require, they are checking like it will works perfectly or not. So it must be equal to our specification. So then only it will pass, and then they will give to public to work with the chips. So this is the main things, front end and back end of the VLSI engineers. So and then so we know that chip inside we are having a transistor, and then we'll move to the types of chips. So we are having the n number of types of chips. Like in the market we are having the microcontroller, microprocessor, SoC, FPGA. So we need to know the difference between the chips. So there are a variety of chips like a ASIC, application specific integrated circuit. This is one kind of chip. And then SoC, system on chip, is one kind of chip. And then MCU, microcontroller, is one kind of chip. And then CPU also one kind of chip. So they are chips, but they are in the different workings. So they are made for different task. They are made for the particular chips are made for the different task and functionalities. So but there is a difference between each and every chips. So CPU, microcontroller, and microprocessors are having different architecture, different things. SoC is literally different from the microcontroller, microprocessor. And then FPGA. So FPGA is also differ from controller, microprocessor, SoC, ASIC. So I think it's till now you guys are getting me. So thank you guys, thank you for joining. Good evening, Naveen Kumar. So okay, so let's see the difference between the chips. So first of all, we need to know what is a microcontroller, what is a microprocessor, and what is a SoC. So what is the ASIC? So what is the FPGA? So these are the chips I know in the market. We having the controller, microprocessor, SoC, ASIC chips, FPGA chips. Okay. So if you take any CPU, so CPU is like it's like a one chip, but it don't have any memory elements inside the chip. So CPU is nothing but CPU is a microprocessor. It's like a microprocessor. So it having only the CPU core. So like a microprocessor cores only inside the chip. So they will follow the some architecture like a ARM architecture, RISC-V architecture. So based on this architecture, they will make the CPUs. So CPU cores are made. That is the main thing. CPU cores. CPU cores. So CPU cores is nothing but it's like this is our brain, I think so. So CPU core, it's based on the architecture. So which architecture means? So which we having the two architectures. We need to follow that only, like a ARM and then RISC-V architecture. So we can divide into two categories of microprocessor, like a RISC type, RISC, and then CISC. So reduced instruction set computer, and then complex instruction set computers. Mostly CPUs are CISC. Mostly microprocessor based on the CISC based architecture. So like a CISC based architecture processor, it having some complex instructions. Our laptop and our personal computers, so the systems are having the CPU cores. These all that particular CPU cores are made by using the CISC architecture. So CISC is nothing but complex instruction set computer. So it will do the serial execution one by one. So it will helpful for the complex executing complex ALU. The CPUs are mostly useful for to do the complex things. So and then coming to this is a CPU. So CPU cores are like a microprocessor cores are made by the ARM architecture, or else RISC-V architecture. So ARM is a main company. So ARM is one company. They will give the IP for the architectures, processor architectures. For example, if you take any chip like a MacBook or Windows or Intel i7, i5, they will use only the ARM architecture design, and then they will buy from the ARM company, and then they will do the customize in the architecture, and then they will make the chip, and then they will give in the laptops. So this is the main workflow of the chips. So basically ARM, the only one company, will give the architecture for the processor cores. All the companies like Intel, AMD, MacBook, they are by the IP, like intellectual property for the architecture from the ARM, and then they will use in it our laptops and computers processors. So this is the main thing of CPU. So CPU, like a microprocessor, it having only CPU cores only, like a processor cores. It don't have any memory elements, counters, DMA, direct memory access inside the chip. So that particular RAM and ROM memory elements are outside the chip only. For example, that if you take any system means in the single PCB, it having the CPU core like a processor core, and then outside the processor core it having the RAM and then memory and then direct memory access modem. So these all things are made in the outside of the chip, so outside of the chip, so there is no nothing in the inside of the chip. So this is a CPU core, but compared to microcontroller it's not like that. So microcontroller it having the memory element and the DMA counters, registers. These all things are comes under in the single chip. So in the single chip only they are made the memory element, memory block, memory access, counters, registers, and then like if you are using the net internet means they will give the modem support inside the chip only. So inside the single chip, so if you build the processor core and then memory and then GPUs, so if you look if inside that single chip, if you are building these things, is called microcontroller. So this is a difference between the microprocessor and microcontroller. So in the microcontroller, so I have some query here. So sir, so when we are making the custom RTOs basic system using, let's say, Raspberry Pi, we should use CISC, right? So risk is one kind of architecture. So I said no, ARM is one company. They will give the architectures like a processor core architecture, and also RISC is a open source like a Ubuntu, like a it's like a RISC is a open source architecture. So you can also use that architecture. You can make the architecture. So you can make the chip based on the RISC-V architecture. So it is our wish. So company will take the RISC-V architecture. It's like open source only. So there is no need to pay for others. But if you take an ARM architecture, we need to pay for ARM company. We need to get the IP for the architecture. So this is a difference. So it is our wish. So if you have one company means you can make the chip like Raspberry Pi. It's like a SoC kind of chip. So Raspberry Pi is a SoC chip. It's not like a microcontroller, microprocessor. It is like a SoC. So Raspberry Pi is a SoC. It's like a mini computer only. So it's like a mini computer. So if you want to make like that chip means, if you are using the RISC-V architecture means you don't need to give money for others. So it is open source. You can follow the RISC-V architecture. So there is no need for to follow this ARM architecture. Follow only ARM, not for RISC-V. It is our wish. We can use anything. So based on our design specification. So based on our chip specification only, we can choose the architecture. So it is our wish. So I think it's understand for you. So and then SoC. So SoC is a main thing. So we are using the mobile phones. So mobile phone, we are all using the mobile phones. So inside the mobile phone it having one chip. Its name is called SoC, system on chip. So system on chip is nothing but it's like a microcontroller, but not like a fully microcontroller. So it having the additional features over the microcontroller. So how means, so for example I will draw the some design. So basically, so SoC is one kind of chip. Inside that it having the n number of CPU cores, like a CPU cores. So sorry, it will take some time. So I will just explain that. So SoC it's kind of a chip. So inside the particular chip, inside the SoC chip, it having the a number of CPU cores. We can build a number of CPU cores, and then it having the GPU. So for example, if you take a normal computer PC, it having CPU in separate and then GPU in separate. So we are making communication like we are making communication between GPU and the CPU by using the PCI protocol, this kind of thing. So but the GPU is outside of the chip, so outside of chip means outside of the CPU core. But here in the SoC, it having the CPU and the GPU, memory, RAM, so like a RAM, and then flash memory, and then EPROM, and then direct memory access, and then these all things are comes under the, are made in the single chip. So in the single chip only we are, if you made these things means, is called a system on chip. So name itself it having the system on chip. So system means we are making the whole system inside the chip. So I will show the example for the SoC. So SoC. So in the single chip, we are making the CPU cores, we are making the GPU, we are making the modem, we are making the DSP block. So in the single chip. So if you imagine, if you are using, if you made these things in the single chip means, we don't need to run for computers. Yeah, we can use mobile phone as computer also. So in future we can achieve that only. In the single SoC chip we can use the phone as like a computer. We can do multitasking, we can do processing, we can do the editing, we can do the rendering. So we can do anything by using the phone, in the mobile phone, but with the some constraints like a speed constraint, and then we need some high per CPU cores. So if you having the more CPU cores means it will execute fast, and then you have to give the GPU high efficiently, then only you will get the fast result. So these are the things, are the constraint we currently we are facing in the SoC. But in the future we can achieve that high speed computing in SoC. So literally if you see like if you are seeing the 5G, so 5G is one advanced technology. So you can also notice that, so nowadays the phones brands are branding their phones like a 5G phone, it having 5G chip. So this chip is nothing but it's not like nothing but SoC. It consists of modem. They are improving the speed of the modem, so they are calling as 5G. So these are the things, and it comes under the SoC. So for example, if you take any processor CPU core, so CPU core like a processor, microprocessor means we can't it don't have any modem inside the chip. We don't It don't have any RAM GPU part inside the processor core. If you take any controller also, it won't, they didn't made CPU cores, GPU cores into the chip. But in the SoC chip, they are made CPU cores, GPU cores, and then modem, internal RAM, DSP block are they made in the single chip. So that's why it's called SoC, system on chip. So the whole thing inside the single chip is right. Okay, right. Karthik Roshan, you are correct only. So our latest technology is SoC only. So mobile phones having the highest functionalities right now. So and then yeah, so why we are using ARM means, so ARM having the AMBA protocols. So AMBA is a bus protocol. So it's like a communication protocol. So I will explain in the upcoming slides. So this is a SoC looks like. So in the single chip, it having the a number of blocks like a GPU block, DSP block, a modem block, and then memory cache, ISP, video processing block, display engine, storage controller. So these are the main components. So main blocks are made in the chip, like it's called SoC. So understand. So till now, do you have any doubt means you can ask now. So it's been half an hour. So if you have any doubt means you can just put in your doubt in chat box. So whole thing inside the single chip, right? Yeah, correct. So and then we'll move to the, so I hope you guys are understanding the SoC, controller, microcontroller and microprocessor. And then we'll move to these are the examples of SoCs like Apple M3, Snapdragon 8 Gen 3, Apple A7 Pro, Nvidia Terra X1. So these are the example for the SoC chips. And then we'll move to the So and then one more thing. So if you take an FEJ, so FEJ is also comes, it's also having the SOC come. So SOC come FPGAs. So SOC come FPGA means, so it's like FPGA chip only, but inside the FPGA chip it having the embedded processors. So embedded core processor. By using the I can use that particular processor. So it's like a SOC kind of FPGA. So I will explain in the upcoming slide. So what is the DSP? DSP is nothing but signal processing, like a audio, video, rendering. That logical that DSP algorithms are performed in this block. So each and every block having some working. So in the display engine, they will that particular block work for displays. So optimize the display, OLED, and then AMOLED display. We are using the AMOLED display, OLED display, and then pixel rate. So and then pixel rate, and then 4K video, 3K video. So these all things taken care by the display engine. Same like DSP. So it will do the DSP operations like a signal processing, like a if you take a machine learning algorithm, and then deep learning. So they are work based on the images and then audios. So CNN algorithm, if you're familiar with the deep learning, there is having the RNN CNN algorithms. So they will that are that particular algorithms are works under the DSP blocks. This DSP block will consist only transistor. So all the blocks are having the transistor only. So this whole chip be made by transistor. CPU core also having transistor, memory cache also having transistor. So all the things made up of transistor only. But in the EPROM, we are having some boot file, some memory, some working file. So that particular file will assign the work for the blocks. So you need to work like this only. So CPU means you have to make the you. For example, if you can take this CPU, big CPU, it will give the instruction for the all blocks of this chip. So CPU will give instruction for the modem. So how means, so CPU saying to modem, so hey, get the 5G network. So and then modem will work for 5G. That that particular modem block will finding the 5G network, and then they will make and then you will get the 5G network. It's like a communication between. So CPU will make the instruction. By using that instruction only, these all blocks are working. GPU, CPU, DSP, and then ISP, and then memory controller, and then storage controller. So DSP is mainly only for doing the image signal processing. So signal means nothing but we can view the signal as image, audio, message, audio. So these all things that comes under the DSP. Like mic. If for example, if you take a mic like a earphone or else how to say, mic and then speaker. So you are speaking with mic, like every phone having mic, and then you are speaking with your friend. So in the same, so it's like we having the high speed technology. So if you say hi in the phone means that receiver also get the same hi message in the same time. So not like same time, so there is a nanosecond or millisecond difference, but we are communicating very fastly. So how it happen means, so every chip it having the mic. So mic will get the audio signals, and then they will do the some DSP operation, and then they will convert into the zeros and ones, and then in the zeros and ones, modem or antenna will transmit to the receiver. The receiver receive the signals, and then they will change the digital to analog conversion, and then speaker will give the output for the receiver. So this is working. So this is working of the chip. So these all instructions are given by CPU only. Okay. Okay, thank you. So these are examples. So and then, so you can notice here, you can ask some doubt here. So what doubt means, you having the n number of blocks like CPU, GPU, lot of blocks, BIMP, MIPI, video processor, ISP. So it having n number of blocks. How will these each and every blocks are communicating? Can anyone respond in chat box? How these blocks? So these all blocks are inside the chip only. How these blocks are communicating each other? So can anyone respond in chat box? So can anyone know about this? So how inside the chip, how the blocks are communicating? So you can respond anything. So I just want to your response. You can guess anything. You can answer in chat box. By bus. So okay. So bus is the correct answer. So bus is nothing but it's like a bus protocol, bus communication protocol. So if you taken anything, so if you taken anything from your computer, mobile phone. So for example, if you taken a USB also one protocol, Ethernet also one protocol. So each and every peripherals you are connecting with a system like a computer, like by using a USB or Ethernet or HDMI or a PCI. So these are the protocols. Yeah, I2C. So there is a two kind of protocols: on-chip protocols, off-chip protocols. So USB, I2C, UART, and then SPI. This all comes mostly under the off-chip protocol. Off-chip means we are by using this protocol. By using this protocol, we can connect the chip and the peripheral device. Understand? So by using this off-chip protocol, we can connect the peripheral device to chip. So for example, UART. So UART is one protocol. It will work based on the baud rate. So it will helpful for the communicating chip to a peripheral device like Bluetooth, GSM, or any sensor. So if you want to communicate with sensor and chip means we need to follow the protocol. You can use anything protocol, any protocol like I2C UART. Most probably for small peripheral device we have to use only UART protocol. For example, IR sensor. So for example, IR sensor or else ultrasonic sensor. So while in the car we are having the ultrasonic sensor. While while if you want to park the car in the parking slot, you have to go back from your car. So you can notice that in your camera window there is one sensor like a, so it will sense a obstacle and then it will measure the distance between your car and object. So if you close to the object, it will blink, it will buzzer. So it will give the buzzer sound to you, indicate that you are the near to obstacle, so you need to just stop here. So this example for the UART protocol. So UART and I2C protocol. So if you want to interface the peripherals like a sensors like a ultrasonic IR sensor, any sensor, if you want to interface to chip means you need to follow the protocols. So understand till now? So how protocols works? So these protocols only for the off chip. So we are looking for the on chip protocols, on chip bus communications. So on chip bus communication is nothing but one like it's like a off chip protocol only. So it having some rules and regulations, so it having some restriction constraints. You need to follow that particular thing only, then only you can get the smooth communication between the chips, in between the blocks in the chip. So the protocols are on chip protocols are mostly called AMBA protocols. Okay, AMBA protocols. So AMBA protocols, so I will show you here. So I just show you some snippet image, so it's just for your understand only. So AMBA protocols is it having three kind of protocols: APP, AHP, and then AXI. So it having three protocols: APP, AHP, AXI. Advanced peripheral bus protocols and advanced high performance bus protocols, and then advanced extensible interface protocols. So these are three protocols: AXI, APP, AHP. These protocols are mainly used for communicating the blocks inside the chip. For example, you can take this an example. So this is a one ARM based SoC, system on chip. So this is one chip. It having the ARM Cortex M0. It's like a processor core. So and then it having power management block, clock generator, UART. So you can see here this is a bus data, it's like a bus communication. It having the AMBA protocol, AHP protocols. So by using the AMBA protocols like AHP, APP, AXI, by these protocols we can make the communication between the blocks inside the chip. These protocols are given by who? So these protocols are given by ARM. So ARM is only one company will having the IP like a patent for these protocols. So I will show the company. Hmm. So advanced microcontroller bus architecture, it having a, so you can see here AMBA developers. So ARM company only having the IP for these protocols. So they will standardize the protocols like they will continuously take care of the protocols. They will improve the efficiency of protocols. They will do the standardization of the protocols continuously. It having a lot of protocols like AXI, Steam, AXI, Light, AHP, ATP, and then ATP. So ATP is one kind of protocol. APP. So those they will have in the protocols working. It's like a IP. It's like a intellectual property. We are using that only. So I think you guys understand. So we can see here APP. So APP, AHP, AXI. There is three kind of protocols. APP for peripheral interfacing, AHP for high performance, high speed interfacing. AXI is for high speed than AHP. So these are the high speed protocols inside the chip. So I have one question. So some interesting question. So if you want to so if you switch on your computer, so you will give the power supply to your computer, you need to boot your OS. So for that, which component will work? Which component? Just a minute. Okay, let's get into the question. So you having your computer, for example laptop or personal computer. So if you want to switch on your computer, you will use the power supply to your CPU core, CPU, and then you will get the supply for CPU. If the only one component must be on, then only you can boot your OS. So I want to know which component must be on, then only your OS will boot, and then you will get the you will work with a computer. So I want to know what is that particular component. If it must be on, then only you will get the then only your OS will boot. So this is a basic component are used for all electronic devices. Flip-flops. So flip-flops. So BIOS firmware. So it's all the BIOS firmware means it having some hardware, and then it will store in the EPROM. So EPROM is the only thing we are storing the BIOS bootable code. It having the boot code in the EPROM. BIOS, anything, if you take any BIOS or anything, that particular boot code are stored in the EPROM. So for EPROM we need one component, it must be on, then only you can execute the you can execute or you can boot the OS. Firstly we need to boot the BIOS, and then that particular bootloader will load the OS, Windows or Mac OS. I think Windows, wrong. So I need to know so all electronic components are based on one thing, like so by using that only we can give the delay in the transistors, by using that only we can give the delay in design code. So I want more guesses from your side. Which component must be on firstly, then only our OS and our bootloader will work. So but you are saying BIOS it's like a bootloader. For that bootloader it need one, yeah, okay, clock. So clock is a correct thing. So Palle Srinu, so thank you for your response. So clock is a correct answer. So clock is very important thing in VLSI. So by using the clock is generated by the clock generator, clock oscillator. So clock each and every electronic device it having the clock oscillator. So if the clock oscillator will work, it's on means. So if the clock oscillator will fail to give the clock pulses to EPROM or bootloader, you won't get anything. So you won't get bootloader will work. So it will stop your it will stop your booting of our OS. So for the accessing the EPROM, so for booting the OS, you need the clock pulses. So the clock pulses are created by the clock generator. So clock generator. So clock generator is the main thing. So oscillator is the, yeah, oscillator. So as same only, clock generator oscillator same. So crystal, so basically crystal. So clock oscillator is important thing to to all the electronic devices. For example, if you take in computer, laptop, any controller, you need the clock pulses. So then only you can perform with chips. Okay. So why clock is important means, so in our real time we are having the time. So we are having like a time means 6 p.m., 10 p.m. So in the particular period, in the particular 6 p.m. I need to take this class. So in this 8 p.m. I have to go to home. So we having know the time. So we having the time for the chips, how to give the delay, how to make the counting, how to you are saying in which in the particular time you need to give output to this input. So based on this giving like a timing measurement, so assigning, so these all things comes under the clock only. So there is one formula is called frequency is equal to 1 by time. Frequency is inversely proportional to time, so it's right. So frequency, so if you are in the high frequency of a clock oscillator, you will get the you will get the high speed performance. Then you can reduce the time, working time. Okay. Speed is frequency is inversely proportional to time. So f equal to 1 by t. If you increase this frequency, if you increase the frequency, you can get the you will achieve the particular task in less time. Okay. So frequency increasing means time decreasing. So if you time increasing means, if you, it's like a vice versa, t equal to 1 by f equal to 1 by t. So okay, so clock oscillator is the main thing. So each and every things are come based on the clock oscillator. So how EPROM will boot the bootloader means, so for that bootloader will actively looking for the clock pulses. If the clock pulses are came for a bootloader, then it will start one instruction. So I know we know that OS based around the okay, I'm audible to you. Can anyone respond to you? I think some disconnection happened. Yeah, APP. So what is APP? So APP is a protocol, on-chip protocol, Advanced Peripheral Bus Communication Protocols, is given by AMBA. It comes under the AMBA protocol, and then this is for interfacing the peripheral devices to chip. Like for example, you are working with some sensor. So chip and sensor we are using the off-chip protocol called UART or I2C. If you take an if you having one sensor, so you having one sensor, so you want to interface with a chip that, so by using the I2C protocol, so you are interfacing chip and the sensor by using I2C protocol. And then inside the chip we need to make the, so these all things come controlled by processor only. So processor, so I will see means I will show you how it works. So good evening. So I will show the some I received some query from your response. What is APP protocol? So APP peripheral. So you can see here. For example, you can take this an example. So this is one chip. It having the processor core, RAM chip, and then I external memory interface, DMA, bridge, APB, UART, timer. So you can see here UART. So UART, it's one protocol. So it will communicating with some chip. You can sorry, it will UART will communicate with some sensor, some small devices, sensor or any UART devices. It's like a peripheral devices. So UART communicating with the peripheral devices by using the off-chip protocol called UART, and then that particular UART data, it having some data. So that particular UART device have to send the data to microprocessor like a ARM processor core. How that data will transfer? By using the protocol only. So this is APP comes under the on-chip protocol. So UART is off-chip protocol. So by UART taking the off-chip protocol, off-chip data from the sensor, and then the sensor data have to given to processor core by using the APP protocol. So APP protocol are making communication between the peripheral devices. So for example, for now UART is a peripheral devices. So UART will communicate with sensor, some particular sensor will get the result, will get the data from any devices like a sensor, anything. So and then that particular data we have to given to the processor, ARM processor. By using the ARM APP protocol, we can make the communication between them. So in between you can see the bridge here. So why it having bridge means AHP, AXI, ASP having the this all high speed protocols in the chip, inside the chip, but APP is a low speed protocol. So how you will measure the high speed low speed means by using the clock only. So AHP and the ASP, AXI are working based on the high bandwidth. So they are high speed protocols. They will work speedily. So they will execute, they will transfer the data very fastly compared to the APP. Why? Because of APP having the low bandwidth, like a low frequency. So it will work slowly. So why it will work slowly means we need to make communication between the UART and the APP. So we need to work slowly only. So UART is a very off-chip protocol, it's very slow only. So we need to make synchronization. For that we are using the APP protocol. APP is a low speed, AHP is high speed. So we can make communication between directly AHP and APP. By using that bridge only, we can make the communication. So we can make the synchronization in the chip, inside the chip. So this is the main thing. So if you want to get more understanding of the chip means protocols means, you will get the free resources from ARM developer. So ARM site only, they will give the specification PDF. So on that particular PDF, it having the all the conditions, all the working of the protocols. So you will get the you will get more knowledge from that. So coming to the FPGA. So till now we seen microcontroller, microprocessor, SoC, and then what? So and then SoC, ASIC chips. So we seen all these chips, but this all looks like a same only. Why? Because of they are depends on architecture. That particular chips depends on architecture, processor core, GPU, RAM, and then controller, OS, bootloader, EPROM. It's all same only. For these all we seen previously, these are similar to each other. So microcontroller and SoC are similar to each other, fine. But FPGA is different from other all chips. Why? Because of we can't reconfigure the microcontroller, microprocessor, ASIC chip, SoC chip. If you made one chip, uh, if you if you taken, for example, if you taken a SoC, Snapdragon 888 is a one SoC chip. So if you made that particular chip, means you can't reconfigure that chip again. Why? Because of you already followed the architecture, processor core, and then you design the memory block, you design the RAM block, you design the MIPI interface, you design the modem. So you can't change anything. If you change, means it will worst thing. So you can't change anything after made the chip. So after completion of the chip, means you can't change anything. So if you made with error, means bugs, means it is error only. So totally cost waste. So but if you take an FPGA, so FPGA is not like that. So FPGA is a field programmable gate array. It's a reconfigurable. It's like a child. So it having the transistor, FPGA having the transistor like logical elements. We can use the transistor as we want. So how means, so it only having the, imagine you having chip, inside the chip it having transistor. So I can use I can reconfigure at every time. So how means, it won't need any architecture, it won't need any particular instruction to do some work. So how means, our OS like Windows and then any Mac OS, they will require instruction set. So instructions, based on the instruction only they will perform, they will work. But here in FPGA we are giving instruction by code. So our while writing the if you are writing the vanilla code, that is the instruction for the transistors. Based on your code only, it will act, whatever you turn in the code, it will act like that only. So understand FPGA. So main thing is FPGA, we can by in the FPGA we can reconfigure the that particular chip. So it means I can build the processor in the FPGA. I can assign the FPGA as a memory element. I can assign the FPGA as the TSP chip. So by using the vanilla code or HTML code, so we can make the FPGA as you want. Understand? So let me know till now you are getting my points. So what is FPGA, how it works? Can anyone respond in chat box? Is there any glitch over there, sir? Glitches. So Karthik Roshan, so what you're asking about? So I had some network issue. So I have some network issue, then that's why only. Yeah, FPGA is reconfigurable chip. Yeah, FPGA is reconfigurable. So that is a main advantage of the FPGA compared to other chips. So we can reconfigure the FPGA. So reconfig means nothing but you having the logical elements, transistors inside the chip. So and then you having the RAM. So RAM block like a flash memory. So in the flash memory, you will in the Xilinx or Vivado, any FPGA tool, Intel Cortex Prime, you are writing the vanilla code. That particular vanilla code are converted into synthesizable code, and then it will convert into gate level netlist. That gate level netlist and then converted into the binary file, bit files. That binary file will flash in the flash memory. So and then it will automatically assign the transistors. So hey you have to do this, and then it having a lot of CLBs. So then just we are assigning that particular tool will make the instruction for the FPGA. This is what you have to do, like that. So I will show in the coming slides. So here, why FPGA custom reconfigurable digital circuits. We can add the peripherals, modify the CPU, speed of the speed for specific computation. So these are the reasons why we need the FPGAs. So and then history of FPGA. Firstly, we having the PLA, programmable logic array, and then we having the PAL, programmable array logic, and then we are having the SPLD. So and then we have CPLD, and then finally we achieved FPGA, field programmable gate array. Okay, so these are the reconfigurable devices. Before the FPGA we are having, so we had that. So this is architecture for CPLD. So this is a main architecture for the FPGA. So inside the FPGA, it having the wires and the transistors. So how we are building the transistor inside the FPGA? So assume that this is one chip. Okay, so assume that. So in the outside of the border, so outside of the chip, we are having the IOs. So IO pins. It's like a physical pins. So in the outside of the chip, it having the IO pins. So each and every IO pins we can use for we can give the input and outputs, and then FPGA. So inside the FPGA, it having the CLBs. So CLB is nothing but it's like a configurable logic block. It having the transistors. So it's like a it having some n number of transistors, and then we can configure that. So how you can work by using the Verilog code. So this is the main thing. So each and every CLBs are connected with wires. So you can see here some lines here. These lines are used to connect the CLBs with IOs. So each and every CLBs it having some blocks like a mux, flip-flops, lookup table. So that particular mux, flip-flop, lookup table are made by the transistor only. So literally it filled with the transistors, but we assign some name like a CLBs. Inside the CLB it having this only. So firstly it having CLBs, each and every CLBs it having mux, lookup table, flip-flops. So and then these each and every CLBs are connected with the wires. So for example, if you write the full adder code, so full adder code means you have to give the three inputs A, B, C in. So if you take this is a one pin for input A, B, C in. So I am using these three pins to give the input for a full adder, and then I will use these two pins to get the output for full adder, sum and carry. Okay, and then so inside the CLB I said no, it having some lookup table, mux, flip-flops. So by using the Verilog code I am assigning. So in this CLB we have to follow this. Okay, in the CLB you have to follow this, and then our code will create our code like a Verilog code, like a text code, like a design code will convert it into gate level netlist, and then transistor, CMOS transistor, and then that particular tool, like if you are using the Xilinx tool, that Xilinx tool will automatically assign that. So you are this particular CLB only for FA, like a full adder. This CLB will do the full adder operation continuously. So based on our inputs it will give the operation, and you will get the output in the IO pins. This is a main working. So it having, so assume if you having the empty like you having chip, it's empty of full of transistor, it's empty transistor. You can say anything to chip. So you need to work like this, that particular chip work like that only. So by using the Verilog code. So this is the working of FPGA. So this is a reconfig. So if you want to do another operation, another task means you can easily you can easily write another code. You can rewrite the flash memory. You will get the another you will give the another task for the FPGA. So and then it will our FPGA will work based on our current task. So this is a reconfiguration. So this is the main thing. So this is the only difference compared to the controller, microprocessor, SoC, ASIC chips, anything. So you can reconfig. So and then moreover FPGAs are mostly used for educational purpose, and then FPGAs are used in the industrial side also. So if you take a Tesla car, for example Tesla car, so Tesla autonomous vehicle or EV vehicle, it will runs based on the battery, like it's a by using the battery power only it will work. So in the Tesla car FPGA are used, where means battery management system. So in the Tesla car, Tesla EV car, they are using FPGA for managing the battery percentage. So if you take an like example, you are seeing in the display, so how many batteries percentage is bending, so how many for remaining percentage is there, full and empty conditions. These all conditions are taken by controlled by FPGA only in the Tesla car. And then there are a lot of example for the FPGAs. So mostly industry, in the industry, like a factories, FPGAs are mainly used to control them, to control, and then to control the motor, to analyze the reports, kind of thing. And also nowadays we can get the SOC kind of FPGA. It's like inside the FPGA we can see here it having a lot of CLBs, configure logic block. So I can assign that. If you I can also give here embedded processor, like a microprocessor. So like if I'm taking like contacts A55 anything, so I can build inside the chip. If I made the processor inside the FPGA chip, means it's called FPGA cum SoC, like it's kind of FPGA cum SoC chip. So it will I can make run the OS in the FPGA. Okay. So for example, if you aware of the Zinc FPGA, like a pink OS, like a Zinc series FPGA given by the Xilinx, it's like a SoC kind of FPGA. It having the embedded processor. So by using that we can run the OS on the processor. Why? Because of we having the processor core. So processor means it will we can make the OS and then we can run on it. Okay. So this is the main thing. So with having the CLBs, logic blocks, and then so this is called configurable logic blocks input, and this is the program interconnect like a wires. So this is what inside the CLBs, lookup table, CLB mux, flip flops, and then clock and reset. So this is the main thing. These are components are inside the CLBs. Okay. Lookup table is nothing but it's like a matrix of storing the inputs of the circuit. If you, for example, if you take a full adder code, means that full adder code, the full adder inputs are stored in the lookup table. So based on our logic, we can use a mux or we can use the flip flops, so we can get the output. Okay. And then so I can assign the FPGA as a DSP blocks. I can assign some CLBs as the DSP block, RAM block, and then this is the FPGA architecture for hardcore processor. It's like a SoC kind of FPGA series. It having the ARM processor core, Ethernet, PCI memory, kind of thing. So we having the Pantech. So Pantech at having the we made the on FPGA board, Max 10 FPGA. So it's powered by Ultra FPGA IC, so Max 10 IC. So we made the development board like this. So this is our board, Pantech. This board is made by Pantech. So I will show in website also. So you can see here we having the so this is our board made by us Pantech. So you can see here. So this is FPGA chip. So this is FPGA chip. It's like it's given by Ultra chip Max 10. The chip name is Max 10. So you can see here it having the lot of peripherals like Ethernet, USB, and then audio codec, and then USB 2.0. This is interface called MIPI interface. MIPI interface is nothing but camera interface and its display interface. So this device are made by the Pantech. So why I'm showing this means I can remove these all things. So I can remove these all peripherals. I can add any other peripherals. So you can see here I have on development board it having on FPGA. So there is no necessary for use only these peripherals only. So I can remove the Ethernet. I can use other peripheral like a sound segment display or servo motor header. So I can add anything. Okay. So this is the main advantage. So I can customize the FPGA. So by using the FPGA IC, I can customize the board. So and most probably FEJ, most probably FEJ are used to industries and also testing purpose of SOCs ASIC chips. Why? Because of for example, you have the ASIC chip, so you made one chip like a you made one chip for AC, so AC controller. So AC one controller, microcontroller. You need to check the getbook. You need to check the IC. So how you can check means you have to give the input like a zeros and ones for chip, and then you will verify the output whether it's correct, whether I received correct or not. So for giving inputs for the that particular microcontroller, that particular chip, FPGA are useful. Why? Because of by tool can't give the real time input for the chip. So but we can give input from the FPGA means it will give the input to testing chip like a test for testing of chip. So we can get conclusion from that. Why? Because of giving input to chip from simulation or tool or any devices means it not suitable thing. So if you are giving the inputs, if you are giving the inputs for your chip using the FPGA means it will good for testing. Why? Because of we can control the FPGA. So by using the we can control the FPGA, and then it means what? So we can give the controlled input for the chip. So based on the inputs you will get the output, and then you can verify that so whether I am correctly receiving or not. So this is a way FPGA are used for post silicon validation also. Okay, so to verify the chips. So and then this is FPGA. So and then the remaining thing is FPGA design flow. So literally firstly we'll see the design flow of the FPGA. So design flow is nothing but this only. So there are the five design flows like a design entry, RTL design and simulation, synthesis, and then implementation, and the testing and the debugging the FPGAs. So testing and debugging. So we'll see one by one. So design entry. So design is nothing but we need to give instruction for the FPGA. For that we have to write the Verilla code or HDL code. Okay. So and then that if you are using the tool like a Xilinx tool, so FPGA is one Xilinx is one FPGA tool. That particular tool will convert the Verilla code into schematics like a logic gates. Okay, so I'll show you. So for if you want to do full adder logic means you need to write the full adder logic like as in someone carry equation, and then you need to verify that. So you need to verify that by using the test bench. And while writing the test bench you will give the stimulus for the design code, and then you will get the output. You can check whether I am correctly receiving or not. So this is the RTL design and simulation. So and then synthesis. So synthesis is nothing but converting the RTL code into Verilla code. So for example, you having AND gate. So you having AND gate. So firstly we need to write the Verilla code for that. It's like a HDL. In the Verilla code you need to write the condition logic for the AND gate. So AND gate is you will do the AND operation. So assign C B A. So these are my inputs. C is input and outputs. C is the output. A and B is the input. Okay, assign C equal to A and B. So A and B is it will do the AND operation and then assign to the C. Okay, this is a design code. So in synthesis we need to check whether my design code is fully functionable and fully convert into the gates. So if you are writing some mistake in the Verilla code, if you can't the tool can't able to convert your code into HDL like a gates means it's wrong only. So the tool have to convert your whole code into logic gates like this. This example this is only simple example. This is AND code for in Verilog. So you need to convert this code into this like a AND gate. So how this conversion will take care by the tool only, but we have to write the code correctly. So why? Because of there is some constraints in Verilog. So there is a lot of rules and regulation, like a synthesizable commands, unsynthesizable commands. So we need to follow that. By based on that only, the tool will convert your whole code into logic gates. So that particular logic gates will assign to the FPGA. Okay. So the synthesis is on this third stage. It will do converting the HDL language into the synthesized AND gate. Okay. It's like converting code to gates. Simple in simple words. So and then implementation. So in the implementation we have to do mapping, place and route. So mapping means, so I already said no, inside the FPGA it having a lot of CLBs. So we need to say, so tool have to say, so in the particular CLB have to work this only, in another CLB have to work this only. And then pin assigning. So inside FPGA having a lot of pins, we have to assign the pins for the input and outputs. Thus this all comes under the map, place and route. So these three things are comes under the assigning the transistors, assigning the CLBs, assigning the IO pins for the design code. Okay. So for the design logic, we are assigning the transistors, IO pins, CLBs, and then wires, kind of things. So and then testing and debugging. So after that, we need to test our FPGA. So by using the simulation and then in circuit testing. So these are the methods. So and then internal structures and FPGA logic, block routing, IO blocks. So we already seen that. So on the logic blocks, it having the transistor pairs, lookup table, multiplexers. It's like a CLB only. So advantage of the FPGA is do anything digital circuit, super fast, field programmable, massively parallel. So it's like, so main thing is parallel. So our CPUs, like a microprocessors, it will do the serial execution. So serial, it will solve one by one instruction. But FPGA is a parallel execution. This is a main thing. That's why it is preferable for the industry grade. So this is a disadvantage: expensive, high power, volatile and boot time, high pin rate, complicated, many traps. These are the disadvantage of the FPGA. So application of the FPGA, they are used in the many ways, like a medical, digital signal processing, video and automotive, data center, aerospace and defense. So there are a lot of applications of FPGAs. So this is a conclusion. So before that, I will show you one thing. So this is Intel Cortex Prime. So this is so we have, there's a two company like Intel and AMD. So AMD is one company. It's like a chip making company. They will provide the Xilinx FPGAs, and the Intel is also one company. They will give they are providing the processors of the to laptops and computers. So they are giving the Ultra FPGAs. AMD giving the Xilinx FPGA, Intel giving the Ultra FPGAs. So AMD giving some separate tool for Xilinx FPGAs. Same thing, Ultra giving the tool, simulation tool or FPGA tool for Ultra FPGAs. Okay, so I'm using the Ultra FPGA. So I chosen the Intel Cortex Prime. So for Xilinx tool, so for Xilinx FPGA, they will provide the Xilinx Vivado. For Ultra FPGAs, we can use the Intel Cortex Prime only. So we can't use you can't use FPGA, like you having the Ultra FPGA, you can't use the Xilinx software. Okay, you have to use only Intel Cortex Prime. So in that I have written some Verilog code for LED blinking. Okay, I'll just show you some Verilog. So this is a module syntax and sample code for LED blinking. So okay, you can see here my input and outputs are, my input is clock and then my output is a LED. So LED one signal. So in the FPGA board, in the particular FPGA, like in the FPGA, maximum FPGA, we having the 5 LEDs. So I need to just blink and off for each and every second. So 1 second off, 1 second on. So we need to give the delay for the blinking. So why? Because of we can't give directly delay for the FPGA. So in Arduino we can give the delay simply, but in the FPGA and Verilla coding, you need to use counter to give the delay. Okay. So I am using the 50 minutes of clock. So in 50 minutes of clock, it will count 55 crores times. So in 1 second, the particular 50 minutes of clock will count 5 crore times, right? Like a 5 crore passages. So imagine how fast it is, 50 minutes of clock. But in simple 50 minutes of clock works this much fast means compared to your mobile phones SOCs. So our mobile phones will works based on the 3.2 4.2 gigahertz. So imagine how it fast. So by using that frequency like a clock inputs only, it will work fastly. Okay, so clock is very important thing. If you are having the high frequency clock, you will get the more speed. Okay, so for example 50 minutes of clock is count 5 crore times. So it will in 1 second it will count 5 crore times. So I know that how means you can calculate by using the formula. So I need time. So t equal to 1 by f. So f means frequency 1 by the 50 megahertz, 50 in the 10 power 6, and then you need to count in the nanosecond. So you have to do some calculation. You will get the 5 crore counts like a 50 millions. So I'll write the if condition. So count equal to 4 crore 99 lakhs and 99 means. So if it is true means I'm just resetting my count and then toggle my LED, and then if it is not true means, and then I'm increasing counting. So it's like a simple if else condition. So I'm continuously incrementing my count. Once if I reach this value, I toggle my LED. So it means 1 second off, 1 second down, 1 second off, 1 second down. So this is working of the FPGA. So this is a simple code. You can see here compile, analysis and synthesis, filter, assembler, timing analyzer, EDA netlist. So these are the compilations. So and then in the tools we can also see the netlist RTL viewer. So this is gates. So I written Verilla code only. This black diagram, this flip flops, and then this mux, this comparator. These are made by the tool, not by me. Okay, these are made by the tool, and then this will convert into binary file. That particular binary file will write into flash memory, and then from the flash memory will work. That particular FPGA will work based on your logic only. So this is the main workflow of the FPGA. Okay, so you guys understand. So do I any doubt from till now? So this is the FPGA. So we can write this. We can write the Verilla code to control the FPGA, and then we have to do compilation. And then it will compile, and then you will get the results. If you have any error, if you face any error means, you can skip. So you have to solve the error, and then you can do recompilation, and then you will get the binary file, and then you have to write into flash memory. The particular flash memory will assign work for the transistor, and then our FPGA will work based on our code. Okay, so understand. Thank you guys, thank you for listening. We'll see another session.